Hello, I'm Youngbom Kim from Dongguk University DTM Lab. Today I'm going to review titled Predictive Modeling for Technology Convergence, a patent data-driven approach through technology topic networks. This is the bibliographic information of the paper. The paper is centered on several key concepts, which are reflected in its keywords: technology convergence, technology topic networks, patent analysis, dynamic topic modeling, and link prediction. These keywords indicate the scope of the study and the methodological tools it employs. The authors propose a novel way to forecast technology convergence by analyzing patent text data. They build a technology topic network using dynamic topic modeling, which tracks how technological themes evolve over time. They then combine text mining with machine learning to perform semantic link prediction. In short, the paper moves beyond conventional IPC-based analysis and introduce a dynamic topic network framework that better reflects innovation trends and helps identify future areas of technology convergence. Here are the contents of the review. This is the introduction of the paper. The authors explain that rapid technological progress shortens technology life cycles, which increases the demand for continuous innovation. At the same time, industry boundaries are becoming blurred, leading to cross-domain inventions. In this environment, technology convergence integrates knowledge from multiple disciplines, creating new technologies, accelerating innovation, and driving future competitiveness. Previous studies mostly relied on patent classifications and bibliometric links. In contrast, this study follows a newer trend using text-based link prediction to provide richer semantic insights. The purpose of the research is threefold: to build technology topic networks from patent texts, to apply dynamic topic modeling in order to track the evolution of technology topics, and to use machine learning-based link prediction to forecast possible technology convergence and support R&D planning. This is the literature review section. The idea of technology convergence dates back to the 1960s, when Rosenberg first observed overlapping technologies across industries. It is generally defined as combining multiple technologies to create new products, services, or systems. Over time, convergence has become seen as a critical factor for industrial growth and competitive advantage. Researchers have studied it using different data sources such as patent, news articles, and even Wikipedia, but patents are the most widely used because they contain comprehensive information about innovation. When it comes to patent analysis, patents provide structured and detailed data on inventions. This makes it possible to track the flow of knowledge and identify important players in technological development. Methods such as text mining and visualization, like patent maps, have been used to reveal opportunities for convergence. More recent studies highlight the need for predictive and detailed approaches, since classification codes alone are not enough to capture emerging convergence trends. Building on this background, the paper sets out to define technology topics with clearer meanings and to develop machine learning models that use technology topic networks to predict where convergence is likely to happen in the future. In this part, the authors focus on technology topic networks. Networks are useful because they show how technology topics are connected within patent documents. Through this, researchers can identify convergence trends, detect emerging fields, and trace the flow of knowledge. Dynamic topic modeling, or DTM, plays an important role here. It captures how topics evolve over time, which makes it possible to detect whether a technology is new, declining, or moving towards convergence. The authors also points out that combining DTM with machine learning improves prediction accuracy. By integrating these methods, researchers can better anticipate potential areas of technology convergence. The table included in the paper provides an overview of previous approaches, comparing different types of network models, text mining methods, and convergence analysis. This slide introduces the proposed approach of the paper. The authors start with collecting data from USPTO patents retrieved through the WIP system. They focus on textual information such as the title, abstracts, and claims. Before analysis, the text goes through several pre-processing steps, including stemming, stop word remover, tokenization, and biogram or trigram modeling. This produces a document term matrix that serves as a foundation for topic modeling. As you can see in the figure on the right, the process begins with collecting and pre-processing patent text data, and then moves into constructing technology topic networks. For this, the authors apply dynamic topic modeling or DTM, which identifies the main technology topics and captures how they evolve over time. Model qualify is measured using perplexity scores, where lower values indicate a better model fit and more coherent topics. Finally, the document's topic and co-occurrence matrices are converted into technology topic networks for each time period. In these networks, nodes represent individual technology topics, while edges represent either co-occurrence or semantic similarity. This network structure shown in the conceptual framework forms the basis for later stages such as feature extraction and prediction. This slide explains how the authors extract features from the topic networks. First, they estimate the likelihood of new links between technology topics. For this, they construct a co-occurrence network where the nodes represent technology topics and the links represent relationships. Link prediction is then applied using proximity-based measures, which helps to estimate the probability of convergence between topics. As shown in Figure 2, the study employs multiple structural proximity indices such as similarity, distinctiveness, and universality. By combining these different measures, the model is able to capture more complex relationships and provide a richer prediction of how topics may connect in the future. The outcome is a set of predicted topic connections that offer deeper insights into emerging convergence trends. In addition to link prediction, the authors also consider causal relationships between technology topics. Using association rule mining, they generate rules that describe directional relationships and with the metal. They identify both direct and indirect causal effects. This makes it possible to distinguish cause topics from effect topics. A key insight is that strong causal links can serve as signals for the main drivers of technology convergence. The next step of the proposed approach is training classification models. The goal here is to predict convergence between topic pairs across different time periods. To achieve this, the authors experiment with a range of algorithms including decision trees, random forest, gradient boosting, naive Bayes, XGBoost, Light, GBM, and KNN. Instead of relying on a single model, they applied an in-sample method using a soft-voting classifier. This approach improves both accuracy and stability by combining the strengths of multiple models while also reducing the risk of overfitting. Once the models are trained, the next stage is to identify potential technology convergence. The models are evaluated using standard metrics such as precision, recall, F1 score, and accuracy. The convergence predictions are then analyzed to uncover emerging convergence trends. According to the authors, the results provide valuable insights that can be applied in strategic planning, innovation management, and decision-making within industry. In other words, this predictive framework not only captures the dynamics of technological change, but also offers practical implications for R&D and policy. This slide shows the experiment setup. The study focuses on biohealthcare technology, including digital healthcare, biopharmaceuticals, medical devices, and related fields. USPTO patents from 2012 to 2020 were collected, and after filtering, about 1765 documents were used. These were divided into 3 time periods for analysis. For pre-processing, the texts were cleaned, tokenized, limitized, and converted into bigram and trigram models. Then, 70 topics were selected to balance perplexity and redundancy, and each topic were assigned to patents with a stable threshold. As Figure 3 illustrates, the process moves from gathering patent data to generating technology topics and finally to constructing topic networks where nodes represent topics and edges represent their co-occurrence. This part represents the prediction of new links in the topic networks. The authors extracted several link prediction features such as record, common neighbors, atomic ADAR, cats, and local pets. For the training data, they compared period 1 to period 2, where 416 topics pairs were initially unlinked. Among them, 65 pairs converged and 351 did not. For the test data, they compared period 2 to period 3 with 299 pairs unlinked. In this case, 34 pairs converged and 265 remained non-converged. As shown in Figure 4, the technology topic networks become denser over time. Each node represents a topic and the growing number of edges reflects increasing interconnections. This demonstrates how the approach can forecast convergence trends by learning temporal patterns in the evolution of topic networks. This slide shows two parts of the results. First, association rule mining generated over 3,400 rules that quantified the relationship between technology topics. As shown in Figure 5, these rules are visualized with support and confidence values, while the dimensional methods revealed both direct and indirect causal effects. Second, the performance of classification models is compared. XGBoost was the best single model with 0.87 accuracy, but as Figure 6 shows, the example voting classifier achieved the most balanced performance, with higher precision and overall stability. In the discussion, the authors summarize how their model forecasts technology convergence in the biohealthcare field. By applying supervised learning on patent data, they identified 9 topics pairs with high probabilities of convergence. For example, the combination of resource management and biosensors suggests the possibility of healthcare and wellness tracking platforms that integrate personalized monitoring and remote care. Another case is the convergence of signal analysis and optical systems, which could form the base for adaptive cognitive optical networks. Finally, the link between voltage control and light or imaging points to opportunities in smart lighting for medical imaging and industrial inspection. As highlighted in section 5.2, these predicted convergences illustrate potential pathways for innovative platforms across healthcare, communication, and imaging. They reflect not only technological progress but also broader social needs for efficiency, personalization, and sustainability. In conclusion, the study highlights several important implications. Anticipating technology convergence can give firms a competitive advantage and support innovation planning. The proposed approach combines technology topic networks, link prediction, and influence relationships within a supervised learning framework. Using ensemble classifiers also improves prediction accuracy compared to previous models. However, there are limitations. Patent data may have quality issues and bias, meaning that all aspects of technological development are fully represented. Another challenge is class imbalance. While overall accuracy is high, the precision of predictions decreases when the data is good. Looking ahead, the authors suggest extending the method to multi-topic convergence beyond simple pairs, incorporating advanced text processing for automatic topic interpretation, and conducting case studies in real industries. They also emphasize the need to develop techniques for handling imbalanced data to make convergence prediction more robust. Thank you for listening to my paper review.